Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. In today's lesson, we are going to do a couple of different things, but we're going to start by looking at the similarities and differences between voltaic and electrolytic cells now that we've done both of them separately. And we're also going to look at something called faradays and cell calculations, where we will be able to figure out, the mass being produced in a molten cell if a cell is running for a certain amount of time with a certain current, etc. So both very important things to know. So let's begin. The first thing I'd like to talk about is similarities in terms of parts between a voltaic cell and an electrolytic cell. I call them the triple E because the three things they have in common in terms of parts all start with the letter E. Number one, voltaic cells, electrolytic cells, both have electrodes. Of course, the electrodes would be made up of the anode and the cathode, but both of those types of cells have to have electrodes. The second thing they have to have is an electrolyte. So an electrolyte is a positive and negative ion that could be either aqueous or molten liquid. So you could have a cation, which is aqueous, an anion, which is aqueous, or you could have a cation, which is liquid, molten, or an anion, which is liquid, molten. The third thing they have to have is an external circuit, which is a fancy way of saying essentially a wire. The thing is, some cells don't use wires, they use metal casings, etc. So that's the triple E. That's what they all have in common. Of course, they also have the same acronyms that we use. They apply to both types of cells. So for instance, ACE, anode to cathode, move electrons. A to A, anions move to anode. C to C, cations move to cathode. Leo Ra, loss of electrons is oxidation at the anode. This is where the reducing agent reacts. And gain of electrons, reduction cathode. OA, we gain electrons and undergo reduction at the cathode. The substance that does this is the oxidizing agent. So those are the things that voltaic and electrolytic cells have in common with one another. Now let's talk about different parts. Now a voltaic cell will have two half cells, whereas an electrolytic cell will just have one cell. Now in order to have two half cells, you have to have some kind of porous divider. So I'm going to say a cup, plug, membrane, salt bridge, U-tube. They have to have some kind of separation that allows for the flow of charge, and those are just a number of different types of voltaic cells you can have. You can have ones with porous cups, porous plugs, porous membranes, salt bridges, U-tubes, lots of different things. Of course, you just won't have that on the electrolytic side as well. Voltaic cells also will usually have a voltmeter in the picture, or maybe a bulb, or maybe a multimeter as part of the picture in the middle of the wire. Whereas in an electrolytic cell, you're going to have some kind of power source. Okay, so there's going to be some power available. In terms of the electric potential values and spontaneity, we know that voltaic cells will have an electric potential which is positive, because it is a spontaneous reaction, which means that my oxidizing agent must be above my reducing agent on the table. Where an electrolytic cell, it's the opposite in all of those ways. So it's not positive, it's negative. It is not spontaneous, it is non-spontaneous. And the reducing agent would fall above the oxidizing agent on the table. In terms of energy conversions, they are again exact opposites. A voltaic cell will take chemical potential energy and will turn it into electrical energy, whereas a electrolytic cell will take electrical energy and turn it into chemical energy. So there's our review of the two types of cells and how they are similar and different. It's very important that you understand all of these similarities and all of these differences going forward. The rest of today's lesson is going to be about calculations that are generally done more for electrolytic cells. They can be done for voltaic, but essentially what we are doing is figuring out how long I have to run a cell for in order to produce a certain mass of a element, for instance, that I want to make. Now, there are two different equations here. There's actually a third one I will introduce that you can use to solve these problems, or you do not need to use any equations at all. So if you're really good at unit analysis, you don't have to remember any of these equations. You can just cancel out units until you get the one you want. And I am going to do a little bit of both. But the first thing I'm going to do is go through these two equations and what all of the different symbols represent, okay? So the first one here is for calculating the number of moles of electrons transferred in terms of moles, like actual moles, not just coefficients, okay? So this stands for moles of electrons. Now sometimes they won't say moles, but amount. In chemistry, amount means moles. It's the exact same thing. So if you were asked to calculate the amount of electrons, that is really saying the same as the number of moles of electrons. The letter I in both of these equations stands for current. Okay, now current has a couple of different units that you can use. An ampere is usually what it's written in, but an ampere is really just the same as the coulombs per second, so charge per second that flows through a wire. T in both of these equations stands for time. Now, the big thing is most questions will give time in minutes, hours, or days because a lot of these cells have to be running for a very long time to produce the amount you want. But when you look at current at its base unit of charge per second, it tells us the unit that we actually need to be in. Time must be done in seconds in this equation, because it has to cancel out with the seconds as part of the ampere. So when I get students to write out their units in their calculation, I never get them to do it in amperes for current. I get them to do it in coulombs per second so that they recognize that the time needs to be in seconds. Now, most questions will not tell you how many coulombs per second you have. They will tell you how many amps the cell is using. F stands for Faraday's constant. Now, Faraday's constant is something that you do not need to memorize. They're going to be given on data sheets. In our data book, it would be page 3, and it's 9.65 times 10 to the 4 coulombs per mole of electrons. Please be very careful here. This is per mole of electrons, not per mole of, say, a solid being produced. This is per mole of electrons. So that's the end of the first equation. I've told you what everything is in this equation. I generally only use the first equation when a question is asking for the amount of moles of electrons transferred. If a question distinctly asks me for that, then I know I'm using this equation. Another way I know I'm using this equation is if the question doesn't give me the mass of a substance or the moles of a substance, say like moles of copper or magnesium or something, which is in this equation here. If I'm not given this, like the mass or the moles, then I have a pretty good idea that I'm going to be using this equation here. Okay, The bottom equation down here is generally used for solving for mass, but it can also be used for solving for the amount of time a thing needs to run or the current. But I write this out in this format, which is a lot different from most teachers. Most teachers would have it rearranged just for mass. And the reason why I have it written out like this is it makes the algebra really easy. Whenever I want to solve for any one of these variables, all I have to do is divide two of the variables to the other side. I'm always just doing one mathematical variation in order to get an answer. And you'll see that when we go do some questions. But first I need to tell you what the rest of these things represent. This E here stands for a mole ratio of electrons to something else. This is the moles of electrons per mole of some substance I'm going to call X. It is a mole ratio that you get from a half reaction. So I'm going to make up an example. Let's say I was making copper at the cathode of an electrolytic cell. So say I had copper 2 plus aqueous plus 2 electrons, and it was turning into copper solid, okay, at the cathode. Then my hypothetical mole ratio would be 2 moles of electrons for every 1 mole of copper. So this would be 2 moles of electrons per 1 mole of X. And in this case, I've just chosen copper randomly per 1 mole of copper. It is a mole ratio from a half reaction. This little m here stands for mass, and this is the mass of X. So it could be grams of X. In our case, this would be grams of copper if I was sticking with the copper idea. And then the capital M stands for molar mass of that substance. So molar mass of X. So this would be grams of X per mole of X. For example, in this problem, if I stuck with copper, it would be the molar mass of copper. There is one more variation of this equation. It's Fen it. And what Fenit is this Fem-mit rearranged, where I bring this M, this capital M, to the other side by division, and mass over molar mass is moles. So if a question, for instance, said, how many moles of copper is produced, I could make an adjustment and use this equation, or I could just figure out, mass over molar mass, and that's going to give me moles. Either way, the equation works. So as a quick review, this is another kind of acronym I use to remember Faraday's law. Fem-mit. And the biggest problem with this is just the fact that there's 2 M's. So I always tell students, Fem starts with a capital letter, mit starts with a capital letter. Now I know where the capital M is. And of course, like I said at the start, we don't have to use either of these equations in our calculations if you just use unit analysis, which is using fractions to solve for a problem. So let's look at probably one of the most famous, most widely used molten electrolytic cells. Remember that a molten cell has no water and that it has just been a melted ionic compound. This allows us to have ions that are able to flow, and therefore the electrolytic cell works. So one of the most famous ones is an aluminum oxide molten cell. This is how we mass produce aluminum, which is one of the most used metals on Earth. Before this process, aluminum was almost like gold in terms of its value because you just couldn't get it. But through these, there are massive factories that have gigantic electrolytic cells, like football field size electrolytic cells that produce aluminum in this way. So essentially what it is aluminum oxide that has been melted, then a power supply is sent through. And so really quickly what we'll do is we'll identify what happens at the anode and the cathode. Now in aluminum oxide, the oxygen here has a -2 oxidation number and as an element at 0. So I can see that the oxygen here has lost 2 electrons per oxygen. And so it would be 6 electrons total. So I know that if you are losing electrons undergoing oxidation, this happens at the anode, this would be my reducing agent. My reducing agent would be O2-. When I look at aluminum, aluminum has a 3+ charge here. And so when it goes from here to here, which is 0, elemental 0, it has gained 3 electrons per aluminum. And I know if I'm gaining electrons, I'm undergoing reduction at the cathode. It's the oxidizing agent. And so Al3+ would be the oxidizing agent. So let's put those into our picture of the cell. I've got Al3+ liquid, and I have O2- liquid. I know that seems really weird, but that's what it is. I will call this side the cathode, just cuz. I'll call this side the anode, just cuz. We'll say they're made of platinum. They're inert electrodes. And so, electrons would flow from anode to cathode through the wire here. The cations would move towards the cathode. The anions would move towards the anode. The Al3+ liquid would gain 3 electrons and become Al liquid. This would then be cooled off to turn it into aluminum solid. Over here we would have O2- liquid. This would lose 2 electrons, become O2 gas plus 2 electrons. And I should say 4 electrons. This would have to be a 2. Good. All right. So that's how the cell would operate. Those are our reaction number of electrons total here. This makes sense. If I was to balance this out, I'd have to multiply the O2- by 3 in order to get my 12 electrons, and the other side I'd have to multiply by 4 to get my 12 electrons. So that's just a review of the molten cell. Let's do an actual problem where we're making a calculation. So here's the first one. It says, if a current ran of 6 amps, so I'm going to write this down immediately. Current is 6.0 amps. I never like to write it as amps though. I would write it as coulombs per second. Is applied for 4 hours. Okay, my time is 4 hours. Now, remember, no time in these calculations is going to be in any other unit than seconds. So this would have to be converted right away. For every 1 hour, there is 3,600 seconds. That is something you definitely should memorize. So the hour cancels out with the hour, and 4 times 3,600 would give us 14,400 seconds. And then it says, then the amount or moles of electrons is. So moles of electrons is what we're looking for. Now, out of the equations we've looked at, the one that fits this is the one that asks for moles of electrons. So moles of electrons is equal to IT all over F. Now, F is Faraday's constant. That can be looked up in a data book. And it's 9.65 times 10 to the 4 coulombs per moles of electrons. So I have everything I need. I just need to substitute it into the equation. This is 6 coulombs per second. I have 14,400 seconds, I'm going to double bracket that. And then I'm going to divide that by Faraday's constant, 9.65 times 10 to the 4 coulombs per mole of electrons. Now what you'll see in terms of the units is coulombs on top is going to cancel out with coulombs on the bottom. This is now 1 over seconds times seconds. The seconds will cancel out. And so now what I'm left with in terms of a unit is 1 over moles of electrons, which will invert to moles of electrons, which is exactly what I'm solving for. So we plug this into our calculator. Okay, and the number of moles of electrons I get is 0.8953 moles of electrons, but with 2 significant digits, this would become moles of electrons would be 0.90 moles. Okay. Now the other way I can do it is using unit analysis, simply starting with whatever unit I want. So I'm just going to do it. It's going to be tight to fit into this area, but I'm going to fit it in. So for instance, I know I want moles of electrons, and so I ask myself, what do I have that's readily available that has moles of electrons in it? And that would be Faraday's constant. What I'm going to do is I'm going to invert this, which I'm essentially saying, rather than saying 9.65 times 10 to the 4 coulombs over 1 mole of electrons, I'm going to invert that. So it's 1 mole of electrons for every 9.65 times 10 to the 4 coulombs. Then I simply ask myself, okay, what has coulombs in it that can cancel out the coulombs down here? Well, current. There's 6.0 coulombs for every 1 second. And so then I cancel out the coulombs, and now I have moles of electrons per second. I don't want that seconds. So on my next fraction, I put 14,400 seconds on top. This is going to cancel out the seconds, and I'm left with the unit of moles of electrons. I put everything on top, hit divide, everything on the bottom, hit equals, and sure enough, it comes out to the exact same value. So either way, it doesn't bother me which way people do it. As long as you're showing your work and you're showing the units cancel out, that's all that really matters. The upside of using unit analysis is there's no equations to memorize, and I don't have to kind of look at a question and say, which of the equations should I use? Because I'm using fractions, I just start with whatever unit I want to solve for, and off I go, I start solving the problem. Okay, here's another question based on the same cell. It says, in the electrolytic cell, the time required for the cell to operate, okay, so let's start with we don't know the time. For the cell to operate at 3000 amps, my current is 3000 amps, but I never use it as amps, I always put it as coulombs per second, to produce a mass of 8.0 kilograms of aluminum. Now, as soon as I know what substance I'm dealing with, then all my other units really have to work around this aluminum. So for instance, I don't care about the oxide here. This is all about aluminum. I'm going to use my aluminum half reaction. So Al3 plus liquid plus 3 electrons becoming Al liquid, because the question is not asking about the oxide in any way. So how is this going to impact my variables and the numbers I'm using? Well, I'm going to get my mole ratio, or little e here, from this equation. I have 3 moles of electrons for every 1 mole of aluminum. So there's the ratio I'm going to be using. 3 moles of electrons for every 1 mole of aluminum. I also know that the molar mass I'm going to be using has to be for aluminum, because this is all about aluminum. So this is going to be 26.98 grams per mole of aluminum. What this has alerted me to is this kilograms isn't going to cancel out nicely with this grams down here. So I'm going to just convert my kilograms of aluminum to grams, so everything is in the same unit. So 8,000 grams of aluminum is the same as 8 kilograms. The only other variable that's missing from my list here is Faraday's constant, which is 9.65 times 10 to the 4 coulombs per mole of electrons. Based on all of these things I have, I know I'm going to be using the Fem-Mit equation. Remember, Fem ends with a lowercase m, and Mit starts with a capital M, the capital M being molar mass. Again, the reason why I have the equation laid out in this fashion, not the traditional way where they have it solving for mass, is because it only requires me to do one algebraic move in order to figure out what I'm solving for. So since I'm solving for time, I'm just going to divide the molar mass and the current to the other side. And there we go. I've done my one mathematical operation to solve for time. I'm going to put that in. So T is equal to FEM all over MI. I'm going to plug those values in, and I'm almost there in terms of getting an answer. So time is going to be equal to Faraday's constant, 9.65 times 10 to the 4 coulombs per mole of electrons, times my mole ratio, 3 moles of electrons for every 1 mole of aluminum, times the mass of aluminum, which is 8,000 grams of aluminum. I double bracket the top, close it off, go to the bottom. I have the molar mass of aluminum, 26.98 grams per mole of aluminum. And that's going to be multiplied by the current, which is 3,000 coulombs per second. Okay, if we look at the units, we'll see them all cancel out but seconds. Coulombs cancels with coulombs. Moles of electrons cancels with moles of electrons. Moles of aluminum cancel with moles of aluminum. Grams of aluminum cancel with grams of aluminum. And now I'm left with 1 over seconds, which inverts into seconds. So the time is going to be equal to, we plug all that into our calculator. And I got 28,613 seconds. Now this question is asking for hours, so I do have to do a quick conversion. There are 3,600 seconds in every 1 hour. So divide my answer by 3,600, and this would be 7.9 hours. So what we're going to do now is we're going to look at a similar type of molten cell, but this one's going to be magnesium chloride in the goal of producing magnesium and chlorine gas. So before we do the calculations, we should first kind of separate this net reaction into its 2 half reactions. So I have magnesium 2 plus liquid turning into magnesium liquid. Now in order to make this work, I would have to balance it out by adding in 2 electrons on this side. So I know that this is gaining electrons undergoing reduction at the cathode, and it's my oxidizing agent. So if there's a question about the magnesium, I know it's coming out at the cathode side of the battery. And then we also have a Cl minus liquid turning into Cl2 gas. That means I need to have 2 Cl minuses on this side and 2 electrons on this side. So this would be losing electrons undergoing oxidation at the anode. The Cl minus is my reducing agent. And if the question was asking about like what's produced at the anode, well, it would be chlorine gas. What was being produced at the cathode would be magnesium liquid. This also gives me my mole ratios. So I'm, 2 moles of electrons for every 1 mole of magnesium liquid, or I could say I have 2 moles of electrons for every 1 mole of Cl2 gas, or 2 moles of electrons for every 2 moles of Cl minus, just in case I need to do any questions with either of those down the road. So the first thing I'm going to get you to look at is A. It says calculate the number of moles of electrons transferred if the molten cell ran for 350 minutes at a current of 12 amps. What I'd like you to do is write down or make a list of all the variables you have. Pause the video now and make a list of all of the information you have and you're looking for. Okay, so what we should have is current, which is 12.0 amps. Of course, I never write it as amps, always write it as coulombs per second. I have time, which is 350 minutes. Now, when I see this, it's brought to my attention, I got seconds and minutes, this isn't going to work. I need to convert those minutes into seconds. So for every 1 minute, I want to get rid of that goes on the bottom, there are 60 seconds. So a quick calculation of 350 times 60 is telling me that this is going to be 21,000 seconds. And then they haven't given me anything else. Now, the question itself is calculate the number of moles of electrons, which makes me think I'm going to be using this equation. Moles of electrons is IT all over F, because again, I have INT, and this has INT in it. It's solving for moles of electrons. The only thing that's missing is my Faraday's constant, which is 9.65 times 10 to the 4 coulombs per mole of electrons. So we'll substitute everything in. Moles of electrons is going to be equal to 12.0 coulombs per second times 21,000 seconds. I'm going to double bracket that to make sure the numerator is done properly. And on the bottom I have 9.65 times 10 to the 4 coulombs per mole of electrons. So I can see seconds will cancel with seconds, coulombs will cancel with coulombs. I'm left with 1 over moles of electrons, which will invert. And so the moles of electrons would be equal to 2.61 moles of electrons. There we go. Okay, next question. It says determine the mass. Okay, we need to know the mass of magnesium liquid. So this is of Mg. Produced in the molten magnesium chloride electrolytic cell if 10 amps. Okay, the current is going to be 10.0 amps, but I'm going to cross out the amps. I'm going to put in coulombs per second. Flow through the cell for a total time of 6.5 hours. I immediately notice that seconds and hours don't really jive. So for every 1 hour, there's 3,600 seconds, and I'm going to do that conversion right away. So this is a total of 23,400 seconds. It says, at which electrode will the magnesium be produced as well? So they've asked for the mass, and they've also asked for the electrode. Now, up at the top, we know that magnesium 2+ gained 2 electrons to become magnesium liquid. So this is gaining electrons. Reduction cathode oxidizing agent. So I know that this is at the cathode. Now, how this half reaction helps me as well is it gives me my mole ratio. My mole ratio would then be 2 moles of electrons, which is here, for every 1 mole of magnesium, which is here. This also tells me that the molar mass must be of magnesium. And so the molar mass of magnesium is 24.31 grams per mole. And my Faraday's constant, of course, is 9.65 times 10 to the 4 coulombs per mole of electrons. I think I'm ready to go. Now, because I did the last FEMMIC question with the equation, I'm just going to show you the rearrangement for that. And then I'm going to show solving the answer using unit analysis, and you can choose either way of doing it. Okay, so if I was to use FEMMIT, I would rearrange this by dividing across the F and E to isolate M. So now I would be M is equal to MIT all over FE. Substituting that in would be 24.31 grams per mole. My current was 10 coulombs per second. My time was 23,400 seconds. I would double bracket the top. On the bottom, Faraday's constant, 9.65 times 10 to the 4 coulombs per mole of electrons. And the mole ratio, 2 moles of electrons for every 1 mole of magnesium. Double bracket that as well, and I can see the units cancel. Moles of electrons cancels with moles of electrons, coulombs cancels with coulombs, moles of magnesium cancels with moles of magnesium, seconds cancels with seconds, and I got grams on top. I might as well just finish off this calculation, and then I'll show you the other way of doing it. And I got 29.474 grams. I need 2 significant digits, so this would end up being a mass of 29 grams. Okay, now the other way of doing it using unit analysis is going to take a little bit of space, and so I'm just going to show you the same thing but using unit analysis. What I would do is I would ask myself, what out of my list of stuff has mass of magnesium in it? And of course, that would be molar mass. So I'm going to actually start with that value. I'm going to say I got 24.31 grams of magnesium for every 1 mole of magnesium. All I'm trying to do is keep this unit around, but always try to get rid of the unit on the bottom. Okay, so for instance, what else has moles of magnesium? My mole ratio. 1 mole of magnesium for every 2 moles of electrons. So the moles of magnesium cancel out with moles of magnesium. Now I got grams per mole of electrons. What else has moles of electrons? I can cancel that out. Faraday's constant. For every 1 mole of electrons, there's 9.65 times 10 to the 4 coulombs of charge. The moles of electrons cancel. Now I have grams per coulomb. I don't want that. I want to get rid of the coulomb, so it goes on the top of the next fraction. So what has coulombs in it? Current. I've got 10 coulombs for every 1 second. So now the coulombs cancels with coulombs. Now I've got grams per second of magnesium produced. I don't want the seconds. What has seconds in it? Well, I have time. There are 23,400 seconds in 6.5 hours. The seconds cancels out. Everything on top goes in one set of brackets, hit divide. Everything on the bottom goes into one set of brackets, hit equals, and sure enough, it comes out to 29 grams as well. What you will notice is when I compare the two methods of calculating this, they are identical. So for instance, everything above that red line is on the numerator. And let's compare the two. So I got 23.41 on top, 24.31 on top. These ones don't affect my answer coming out. I got 10 on top, 10 on top, 23,400 on top, 23,400 on top. My numerator here is the same as my numerator on here. They're exactly the same. When I look at the bottom, these ones don't affect the value coming out, but I do have 2 on the bottom, 2 on the bottom, faradays on the bottom, faradays on the bottom. So the denominator here is exactly the same as the denominator here. It is the exact same thing, it's just work shown in a different way. Again, whatever you feel most comfortable with, whether it is using unit analysis or the equation, is fine. My preference is the unit analysis, just because then I don't have to memorize an equation, and no matter what type of problem I have, I can always figure out an answer. I'm not trying to decipher which equation to use. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.